Welcome to Chapter 17, which is really a continuation of Chapter 16. Chapter 16 was all about acids and bases, and Chapter 17 is all about buffers and titrations, which have everything to do with acids and bases. So let's start with buffers. A buffer is a solution that resists change in pH because it can neutralize both acids and bases. So in other words, I like to usually do a demonstration in class where I have two beakers, and one contains just pure water, and the other contains a buffer. And if you add just 1 or 2 drops of strong acid to the water, it will go from a pH of 7 to a pH of like 2. That pH will drop precipitously when you add acid. But if you add that same acid to this buffer, and let's say the buffer is also a pH of 7, all right, you add those couple of drops of acid, and the buffer is has a pH of 6.9. So its pH does not change. It resists change in pH when you add acid. Same thing if you add a base. So the magical components of this buffer are that it contains both a weak acid and a weak base. And in that way, it's able to neutralize whichever you add, acid or base, to the equation. So it could contain either a weak acid plus that acid's conjugate base. So we sort of abbreviate that as HA and A minus. Or it could contain a weak base and the conjugate acid of that base. So basically it contains a weak conjugate acid-base pair. So an example of one is acetic acid, HC2H3O2. That's a weak acid. And its conjugate base is C2H3O2 minus, okay? But in order to add that ion, you can't go to your chemical cabinet and find, a container of ions. Chemicals don't exist in dry form, in ionic form. So usually if we're adding that ion, we're adding it in the form of a salt. So maybe we would add sodium acetate or potassium acetate. All right, so it'd be in some salt form. And the salt, when it goes into solution, of course, is going to dissociate into that anion. All right, so if we were to take this solution of acetic acid and sodium acetate, and we added acid to it, all right, let's say we add a strong acid, hydrochloric acid, to this solution, all right, it's going to react with the conjugate base, the C2H3O2 ion, and form HC2H3O2 and Cl minus. So that proton from the acid donates the proton to the base. All right, and so that neutralizes it. So we don't end up with any H plus. All right, any of the H plus that forms gets basically consumed by this weak base here. So the pH does not change. All right, if we took that same solution and we added a base, let's say sodium hydroxide, common strong base, it's going to react with the acid, HC2H3O2, all right, and the acid will donate the proton. So the NH, of course, is going to dissociate into, the NaOH will dissociate into Na plus and OH minus, and that OH minus will gain a proton from this acid. So we'll end up with the base, the weak base, C2H3O2 minus, plus some Na and some water. All right, so this weak acid is neutralizing any base that forms, any OH minus, and we end up neutralizing it to water. So there's no change in pH again. So this buffer solution would look like this. It's basically a weak acid and a weak base that are in equilibrium with each other. Because remember, a weak acid and its conjugate base are part of an equilibrium equation. And if we start out with the same amount of each, okay, then when we add acid or base, all we're doing is sort of shifting the equilibrium a little bit one way or the other. So buffers keep pH steady, but an important thing to know is that they aren't necessarily at a neutral pH. So in my example up here, I showed you that the buffer was at a pH of 7 because we were comparing it to water. But you can make buffers that are set at different pHs. So basically, if you have a condition, if you are running a reaction and your enzyme works best at a pH of 2, then you would want a buffer that holds the pH steady at a pH of 2. So buffers can be created at any pH, and the key is that they keep that pH steady. It's not that they keep the pH neutral, it's that they keep the pH steady at whatever the pH is. Okay, so how do we determine the pH of a buffer solution? Well, there's an equation for that. It's called the Henderson-Hasselbalch equation. Henderson-Hasselbalch equation, and it looks like this. The buffer pH is equal to the pKa plus the log of the concentration of the base over the concentration of the acid, and that's of the conjugate acid-base pair in the buffer. pKa is new, but remember that P always stands for negative log, so pKa is just the negative log of the Ka of the acid, whichever of this acid here. And another thing to know is that pKa for an acid plus the pKb of the conjugate base equals 14. When you have a conjugate acid-base pair, the pKa, the negative log of the Ka, plus the negative log of the Kb will equal 14. All right, and so let's do a practice problem. It says calculate the pH of a buffer solution that is 0.05 molar in benzoic acid and 0.15 molar in sodium benzoate. So this is our weak acid, and this here is our conjugate base with a sodium added to make it into a solid salt. But in solution, it will dissociate and we'll end up with just this part as the conjugate base. All right, and it gives us, the Ka of benzoic acid is 6.5 times 10 to the negative fifth. All right, so I didn't leave room on this page. We're going to the next page for the work on this problem. We're using the Henderson-Hasselbalch equation, which is, a reminder, pH equals pKa plus the log of the concentration of the base over the concentration of the acid. And you don't have to memorize this equation, but you do have to be able to use it correctly. So the pKa, so pH, in other words, equals the negative log of the Ka. That's what pKa is. And we're told that the pKa here is 6.5 times 10 to the negative 5, plus the log of the concentration of the base, which was the salt, and it was 0.15 molar, over the concentration of the acid, benzoic acid, 0.05 molar. So that is the negative log of 6.5 times 10 to the negative fifth is 4.19. It's a positive number. And 0.15 over 0.05 is 3, so that's going to be plus the log of 3. And that is 4.19 plus 0.477, which equals 4.67. So the pH of this buffer solution is 4.67. Here's another one. You can try it on your own and check your answer when you're done. Calculate the pH of a buffer solution that is 0.5 molar in NH3 and 0.2 molar in NH4Cl. And it tells us the pKb for NH3 is 4.75. Okay, so we're using this Henderson-Hasselbalch equation. pH equals pKa plus log of base over acid, concentration of each of these. Okay, so the important thing here really is identifying what is the base and what is the acid. All right, in this problem, it tells us we have a pKb for NH3. So that tells us that NH3 is the base. We can also look at our table and find NH3 and find that it's a base. It's also just a very common weak base that you probably will have memorized if you don't already. And NH4Cl is a salt. This is an ionic compound that breaks up into NH4 plus and Cl minus, and this is the conjugate acid of NH3. So this is our acid, and this is our base. All right, so it gives us the pKb, but we need the pKa, right? So the pKa, remember pKb plus pKa equals 14. So pKa plus 4.75 equals 14, which means that our pKa is 14 minus 4.75, so it's 9.25. So we can plug that in here. All right, pKa is 9.25 plus the log of the concentration of the base over the concentration of the acid. Which is the base? That's the NH3. So that's 0.50, and the acid is this guy over here, so 0.20. And the log of 0.05 over 0.2 is 2.5. So we get 9.25 plus 2.5 equals a total of 11.75. That is our pH. The pH here is 11.75, which makes sense if we eyeball this because the concentration of the base is higher than the concentration of its conjugate acid, so I suppose we'd expect it to be a basic pH. All right, so these problems are good illustrations of how you can have a buffer that is a conjugate, that's a weak acid and its conjugate base, or it can be a weak base and the conjugate acid. Either way, you're using the same equation to figure out the pH. And the pH is rarely 7. It can be 7, neutral, but it can be anything. And there are different scenarios where you want a pH of a buffer solution to be acidic or basic. So, buffers and their effectiveness. A buffer's effectiveness is basically how well does it maintain its pH. That's the whole point of the buffer. Is to keep a steady pH. So the two things that make it most effective is one, it's most effective when the concentrations of the acid and conjugate base are equal. All right, so that they are close together. So basically, you want this ratio here, the concentration of acid, or concentration of base over concentration of acid, to be close to 1. The closer it is to 1, the more effective that buffer is. The more effective it is at keeping the pH steady. So the general rule of thumb is when you make a buffer, the relative concentrations of the conjugate acid-base pair should not differ by more than a factor of 10. All right, they can be a little bit different, like 0.5 and 0.2, which we saw before, but it shouldn't be more than 5 and 0.5. All right, so they shouldn't be more than 10 times off. The second thing that makes a buffer effective is when the concentrations of the weak acid base pair are high. All right, not a dilute solution of the conjugate acid and base, but a fairly concentrated solution. The more dilute the buffer is, the less effective it is. And that makes sense if you think about the fact that those weak acids and bases, they neutralize anything that you add. So the more of the weak acid and base you have in that buffer, the more acid and base you can neutralize when added, the more effective the buffer will be. So this is just a concept check question. If we consider a buffer that's composed of the weak acid HA and its conjugate base A-, then which of the following sets of concentrations results in the most effective buffer? So we want them to be roughly equal to 1, and we want them to both be fairly high, the concentrations to be fairly high. So this one, let's say A here, it satisfies rule 1, but maybe not rule 2. It's this is a relative question, so we're asking relative to each of the other answers. And I'm looking at the other answers, and 0.1 is the lowest concentration of them all. So it doesn't really satisfy rule 2. Now rule B, okay, it does satisfy rule 1, but it is not equal exactly, but it is within that factor of 10, okay. Rule 2, this one is high, but this one is low, so I would say it maybe kind of satisfies rule 2. For C, it does satisfy rule 1, they are equal, and for rule 2, it's a higher concentration than A, so that's good. It's not as high as 0.9, but it is higher than 0.1. And if we look at these other ones, all right, that concentration of 0.1 is always lower than 0.5. So I'm going to say C. C here would be the best buffer of the 4 different choices because it has a base and acid ratio. They have equal concentrations of the weak acid and the conjugate base. And compared to the other options, it has a higher concentration. Okay, so that would be the answer there. All right, a third thing that is important about a buffer is that buffers sort of have a range where they can stay within. If you have a buffer that has a pH of 7, all right, it's effective until the pH gets down to about 6 or up to about 8. So that's what we call the effective range for a buffering system. So it's 1 pH unit on either side of the pKa. So the pH, no, sorry, I just totally messed up that explanation. Okay, so when you are designing a buffer, forget what I just said. When you're designing a buffer and you have a certain pH that you want to pick a conjugate acid-base pair where the pKa of the acid is close to the pH that you want to have. So let's say you want to make a solution that has a pH of 7. You want to make a buffer with a pH of 7. Then you want to pick an acid that has a pKa of 6 to 8. Okay, that is the right acid to use to make this buffer. Same thing, if you want to make a buffer with a pH of 3, then you'd want to pick an acid with a pH of 2 to 4. All right, those are make the most effective buffer systems. So, concept checked. Which acid would you choose to combine with its sodium salt in order to make a solution that has a buffer pH of 4.25? All right, so it gives you 4 different acids and 4 different Kas. All right, we could calculate the pKas of all of these. I'm going to just do some estimations. So based on the exponent here, this pKa is going to be about 2. This one will be about 4. This one will be about 4. And this one will be about 8. All right, so we can rule out this one and this one. We want one that has a pKa that's close to 4.25. So we can now, if you need to, you can get out your calculator and you can calculate which one's going to be closest to 4.25, which I will do, even though I can do this in my head. Okay. So technically, actually, either of them would be okay, but we'll calculate it out to see which one would be best. So 4.57 EE negative 4. The negative log of that is 3.34, and 1.82 EE negative 4. The negative log of that, this one is 3.74. All right, so both of these are within plus or minus 1 of 4.25, but this one is closest, so this would be the best one to use. Technically, you could use either one, though. All right, so that's a simple question that you might find in the homework, is just which acid would be best to make a buffer of X pH. And all you're doing is looking for the Ka, the pKa, technically. But a lot of times you won't be given these Ka values in the problem. You will be expected to go look them up on that table. So always have that table of acids and bases and the Kas and Kbs handy for you. All right, so another thing having to do with buffer effectiveness is something we call buffer capacity. So basically the way to sort of conceptualize this is if you have a buffer at pH 7, all right, and I said when you add a couple of drops of acid, it goes down to a pH of 6.9. Okay, so the buffer capacity is basically how much acid can you add before you really get a change in the pH, like a significant change, before you lose the ability of this buffer to neutralize the added acid. All right, so it's the amount of acid or base that we can add to a buffer without causing significant change in pH. So we've got this concept question here. All right, a 1 liter buffer solution is 0.1 molar in hydrofluoric acid, HF, that's our weak acid. I'll put an A here. And 0.05 molar in NaF, F minus of that salt being the conjugate base. I'll put Cb. So which action will destroy the buffer? So in other words, we have 0.1 molar of the acid, all right, that can neutralize 0.1 molar of some added base. All right, and we also have 0.05 molar conjugate base in our buffer. So that will be able to neutralize 0.05 moles of added acid. All right, and I should say moles. All right, because we have a 1 liter, this is 1 liter, so that means that 0.1 molar is 0.1 moles. That in this concentration, that 0.05 molar means that we have 0.05 moles because we have that many moles per liter and we have 1 liter of the solution. Okay, so we can neutralize a maximum of 0.1 moles of base. So NaOH, that is a base. So could we add 0.05 moles of base? Yes, we could. This would be kosher, all right? That would not destroy our buffer. That is within the range or the buffering capacity of our buffer. What about acid? We can neutralize a maximum of 0.05 moles of acid. And HCl, all right, is if we add 0.05 moles of acid, all right, that's the max. That's the max that we could add, okay? So if we added that much, we would destroy the buffer. It would no longer have any more buffering capacity. And we certainly could not add any more than that. So this is the answer it's looking for. But let's also look at C here. If we add 0.05 moles of NaF, all right, if we did that, that's part of our buffer system, all right? That would actually improve our buffer because then we would have the same concentration of our conjugate base and our weak acid. So this would actually check plus, I would say. That would actually make the buffer better, have a stronger buffering capacity, all right? So this one the B would weaken the buffering capacity, but A would destroy the buffering capacity. It would max it out. That's the maximum amount of acid that can be added, and you wouldn't be able to add any more. So that's what it means when it asks which action will destroy the buffer, which one will max out the buffering capacity. All right, so I'm going to go through one more concept on this next page, and we're actually backtracking a little bit to Chapter 8, as we did sort of before, because remember, Chapter 8 is actually where acid-base reactions were introduced. So I've already been kind of referring to this concept that acids and bases neutralize each other, all right? So when I showed you some of those buffer reactions before, I was showing you that the H plus from the acid that's donated by the acid can react with an OH minus that's from the base, and they then will form water, all right, which is neutral. So that's why we call it a neutralization reaction. Neutralization reactions. So when you mix an acid and a base, it's just called a neutralization reaction. Sometimes it's called acid-base reactions, but more commonly, it's called a neutralization reaction because the H plus and the OH together, the H plus from the acid, the OH from the base form water, which is neutral. Then the cation from the base and the anion from the acid will get together and form a salt. So neutralization reactions are basically double displacement reactions. It's what happens between an acid and a base, and the product is always water and a salt. So some examples. Let's take hydrochloric acid, aqueous, and sodium hydroxide. This is a classic one, all right? Classic strong acid plus a strong base. All right, this is our acid and our base. All right, and they will react to form water, and that water came from this OH and this H from the acid, and then a salt, in this case, the cation from the base and the anion from the acid. So sodium chloride is the salt that's formed, and that will be aqueous in solution. So remember, a salt is any ionic compound. It's not necessarily sodium chloride. So let's do another one. We've got HF. This is our acid. And we'll do potassium hydroxide as the base. And sorry, this should not be an equilibrium arrow. It should just be a one-way arrow because they're both strong acid and strong base. All right. So this one has a strong base, so this one's still going to be a one-way arrow. It's going to form water and a salt. So the water came from this OH and this H, and then the salt is going to be from the fluoride ion and the potassium ion. So we have to remember our salt-forming, our ionic compound-forming rules here, that the cation is the potassium, and the anion is the fluorine. So we always put the cation first and the anion second, and the charges have to equal and cancel out. And in this case, they do. So the salt that forms is just KF. All right, but sometimes we need to add subscripts. And so let's do one more before we get cut off. HNO3 plus barium hydroxide, so that's nitric acid plus barium hydroxide, all right, is going to form water from the OH minus and the H, and the salt that forms is going to be from the barium and the nitrate. Barium has a 2+ charge, and nitrate has